Now let's have a closer look into the LTE architecture. Might look confusing, but I think you're now used to that, looking at the other architectures of UMTS, GSM, etc. already introduced. So the LTE architecture consists of the E-UTRAN, so the Evolved UMTS Terrestrial Radio Access Network with all the cells, the E-Node Bs, no more separate network controller. So the E-Node B comprises the old Node B, so the base transceiver station, and the old radio network controller, the base station controller, the other standards, now with new functionality. So that's something new. That's the first thing we notice, no more separate network controller. I will come back to the components on the next slides in some more detail. What else? We see that we have a network, if required, between the E-Node Bs here in our E-UTRAN network. So it's not any longer this hierarchical tree-like topology from the core network to the radio network. So we see now more kind of a meshed network. Okay. We see our user equipment connected to exactly one antenna, not like in UMTS, the separate antennas. So there's no splitting of the streams and merging of the streams. It's not a CDMA technology here any longer. So we have a mesh, we have connections between the E-Node Bs. They all have names like X2, user and control, but that's not that important. So the network, the UTRAN network, looks different. Not this tree, more this meshed network. What else do we see? In the core network, it's now called the Evolved Packet Core, only packet switching. So it's similar to the GPRS part of our GSM network. So it's a packet switching network. We see signaling, that's the dashed lines connections, and data transfer, the solid lines. So if whatever UE2 transmits data, it could flow, for example, like this into the internet. So the E-Node Bs can forward the traffic, and inside the core network we have the routers forwarding traffic. What else do we see? We see a mobility management entity, I will come back to this, connected via signaling with other E-Node Bs, as you see here, controlling them. An E-Node B can be also connected to more than one MME, so there's a higher flexibility. So in case of component failure, we do not have a single point of failure. Compared to the UMTS or GSM network, if a radio network controller fails or a MSc fails, then the whole subtree connected to this MSc fails. And here we could switch over from one MME to another MME. That's one of the ideas. So the MMEs, that's more or less something functionality similar to our visitor location register. So we have a database, we know who's where. We have some so-called gateways that are our routers, so serving gateways, and we have the gateways then to the other networks, our packet gateways, routers that forward packets as we know it from the internet. That's basically the same. And then we have databases, the HSSS, the home subscriber server. That's something like our home location server, and we might have connections to old networks, etc. So you see, if you know the old architecture, you see some of the differences, but also similarities. Let's have a closer look. So the Evolved-UTRAN contains only the E-Node Bs. There are no more controllers, and the E-Node Bs are now responsible for radio resource management, managing quality of service, interference, controlling the admission, who is allowed to participate in the network, signaling the measurement of the signal strength. That's quite important for handover, resource allocation, scheduling, so which packet to pick now to transmit. depending on the quality of service we want to guarantee. We want to guarantee a bit rate, we want to guarantee a maximum delay. You learned already a bit about the delay budget. We do encryption here, etc. So this eNote B now comprises this old Node B plus radio network controller functionality now for LTE. And the reason is reducing latency. The more components you have in a network, the higher the latency is, so reducing components reduces latency. The UE now, the user equipment, communicates only with one eNote B. Here, just shown here, that's called the serving eNote B. The connection to the packet core goes either via the S1 connection. We have a user connection, S1U, and signaling, S1 MME. It could also, the data flow could also be via other eNote Bs. Then we use the X2 interface, again, user and control. We can also have a eNote B at home, a home eNote B, so we can create a femtocell at home. That's also possible. And then you can have a more or less smooth handover from your home cell into a public cell. The same device, so and you will not really notice it. So that's quite clever idea to have this kind of seamless change of the network from the public into your own home network, and then this can be connected to your internet access point. So that's one of the ideas. Looking at the core, the Evolved packet core, you will find, well, almost familiar entities, mobility management. So that's the component that performs all the signaling between user equipment and the Evolved packet core. That's used for security, handling of the mobility of the devices. And also you have to check the bureau of the traffic flows. So you have a control function, and this MME is also, or the MMEs, they have their connection, it's all packet oriented, to the home subscriber server, something similar to the home location register. There we have all the subscriber information. So am I allowed to access a certain packet data network? What is my QoS profile? What maximum data kind of a traffic plan? Whatever do I have? Roaming restrictions, etc. This is also where I store the current location and the MME responsible for the user equipment. And we also have an authentication center. So pretty similar to UMTS. What else do we have? A serving gateway. That's, well, the mobility anchor for the IP packets, the user IP packets. I will show you the protocols in a second. There we also have to buffer our packets while paging the user equipment, because we have to page them. So if we hadn't have a connection to the UE for a longer time, then we have to page it, similar to what we know from the second, third generation. And during that time, we have to buffer data. This way we can also collect charging information. This the point we have to perform the lawful interception, so if you want to intercept traffic flows. Okay, what else do we have? A gateway to other packet data networks. So that's where we have this IP address allocation. So we have to have IP address, packet filtering, quality of service enforcement. So we have to limit maybe the data rates, etc. Additionally, we have a function that is called a policy charging rules function. This is needed for, well, policy control. Depending on your subscription, you're allowed to do this or that, and we have to monitor this somehow. We have to control the charging of data flows if we charge per data flow, depending on whatever subscription again. So there's a certain function. There are some more functions like earthquake and tsunami warning function, etc. are not shown here. So this is a certain high-level view on the architecture. Okay, and then we also find protocols, well, familiar to you. That pretty much looks like the protocols we had for UMTS, but no more circuit switching, only packet switching. We have similar protocols, tunneling protocols. We use IP, and if you transmit data using TCP, then your TCP is here, and then you have this virtual channel across the whole infrastructure until you reach this PDN gateway. That's for you, that's just basically a router, and then you're out in the internet. And you will not see the underlying eNode Bs and all the other gateways in between. But that's pretty much similar to UMTS, to similar also GPRS architecture. And here you can see how you can save money, because it costs a lot, the investment in the infrastructure, and if you can at least reuse roughly the architecture, if you can perform certain software updates, then also hardware updates from time to time, it's way better than to have a revolutionary approach that comes with a complete different architecture. Okay, so a bit about the architecture, about the protocol stacks. LTE now uses FDMA, TDMA. So, and at the core, you will find a TDMA radio frame, a radio frame with 10 milliseconds, certain subframes. I will not go into the detail of the subframes. If you're interested, please do have a look at the standards, at many tutorials, books, videos about this, because as soon as we dig into these subframes, this is more and more electrical engineering. Then we end up with OFDM, how this works, how you really distribute your user bits into the subframes, etc. We will stay here on a computer science level, that you have a basic understanding of LTE, but we skip all the electrical engineering part when it comes to signals. So we have a FDD, we have a TDD scheme, uplink, downlink, certain synchronization, I will come back to this, necessary, radio frames 10 milliseconds, so no more CDMA as I said, but now back again with certain slots, but the user data is distributed in a different way. So we do not have a time slot per user. So not at all. So that's handled in a different way. So we, as you see here, we have radio frame 10 milliseconds, subframe 1 millisecond. I will come back to this subframe on the next slide. In the TDD scheme, we switch downlink, uplink. Well, it's using the same frequency, so it's unpaired band, and FDD, we see these classical paired bands. So with the separation of the direction by frequency. Okay, looks familiar, although the function is different when it comes to the time slots. But now what is really different? How do we really do the access? Well, as I said, no more CDMA. Now scheduling of the different user equipment is in time and frequency. And this is a very, very, very simplified figure showing you this. So LTE knows certain resource blocks. A resource block is a part of a spectrum for a certain amount of time. These are the slots in our radio frames, 100 our 10 millisecond, now 1 millisecond. For 1 millisecond, we can assign a certain part of the spectrum to users, here shown to a single device. So 180 kilohertz for 1 millisecond. That's a resource block. We can do a lot more inside these blocks, but we'll skip this. Now the idea here is roughly we allocate different parts of the spectrum for a certain amount of time, slotted here in this 1 millisecond packets, for different user equipments. So this is how we can adapt to different data rates. So we can use more of the spectrum. We can use less of the spectrum. We can also change the way we do the modulation, not shown here. We can also assign a certain part of the spectrum for longer time, for several resource blocks. We can do a repeated assignment of resource blocks. This is one way of guaranteeing data rates. If you just repeat a certain pattern of allocation, then we can easily schedule data streams with a guaranteed data rate. So in the end, it's up to the eNote B to perform this scheduling inside a cell to allocate resources. Resources means time slots and part of the spectrum to certain devices. So that's very roughly the idea here. No more code multiplexing, but a pure frequency and time multiplexing, but we use the orthogonal frequency division multiple access, OFDM. Here, that's a scheme I introduced briefly in the very beginning when we talked about multiple access signals, etc. If you're interested in more details, there are very good tutorials, video clips about how you then in the end map your user bits onto so-called symbols, then OFDM, how you perform this, how you apply this. But this really goes into electrical engineering, and do this only if you're interested in these details. Otherwise, for us, it's enough to understand, okay, way higher flexibility by a dynamic allocation of time and parts of the spectrum. So that's the key idea of LTE when it comes to multiple access. Okay, so now we are back at TDM. We have slot structures. We need precise synchronization. That's something we did not really have at the CDMA UMTS scheme. There we used CDMA to separate the users. Now we use here again our time slots. And as soon as we have time slots, we again run into a problem of synchronization. So this TDM part requires again alignment in time. That's something we learned already with GSM. There we had the time advanced field, and something similar is needed here. The further away a user equipment is from the eNote B, the earlier it has to transmit. So we have to configure the devices at a certain granularity. You see here 0.52 microseconds to adjust the sending, earlier sending between 0 and 0.67 milliseconds. And that again corresponds to a certain cell radius. That's how we come to 100 kilometers. You remember GSM 35 kilometers. That means if your eNote B sends packets, you will receive the packets with a certain delay. So you send certain delay. For all the packets, you have this certain delay. And this delay varies over time. It's our T1, depending on the distance. So you can measure and the delay. You will see, okay, there's a slight delay. But also the eNote B can tell you the time difference, because the eNote B will also receive your packets with a certain delay, well, relative to the synchronization. If you're further away, well, the delay is more. Now in the end, we have to adjust the sending. That's the important part. The sending of your packets. Receiving is it's not a problem, because that's only for you, but the sending is a problem. To avoid overlapping in time at the eNote B, exactly the same as we had in GSM. So we have to send earlier so that the packets arrive in sync, or way earlier so that they also arrive in sync. They can arrive at the same time, they're separated in spectrum, etc. So that's to just indicate that now, as we are back at the TDM scheme, we have to do this timing alignment. So again, we have a time advance. Okay, the advantages, we do not have this tight power control, so 1500 times per second in UMTS, and now we are back at something like 200 times per second. So that's way better, because tight power control consumes power. What else is similar but also different? Well, handover. How does handover work? We learned GSM has a hard handover. UMTS has a soft handover due to the CDMA. Now we are back at a hard handover again. But there's also a difference. So hard handover because we have to hand over a connection from a certain time slot frequency to another time slot frequency at another eNode B. So if the user equipment goes from one cell to another, we have to perform a hard handover. There are two different handover schemes shown here in the slides. So we move from one eNode B to another one. And now the UEs, the mobile stations, they perform measurement of the signals as we're used from the other standards. Sooner or later, the network will decide we have to relocate the device because the signal from one node gets weaker and weaker and weaker, similar to what we know from GSM. So we have thresholds to avoid ping pong and all these things. So step one is we have to decide now we will relocate. And the decision is made by the network. The user equipment can tell, okay, I want to, well, this is the signal strength. Now please do something. The network will decide, okay, and send this handover required. That's the signal message. So to our MME, the source MME, this would be in our example, our source here. So the source and the source MME will then check with the target MME, could be the same MME, in this case it's a different one, the target, if this works. So you have to check with the other, that's our target, if this really works. Okay, and then we need certain resources. We have to set this up at our target eNode B. Do we have the resources, etc.? If yes, we know this, okay, everything works well, then we say, okay, now please do the handover. So we tell the source MME, now we can perform the handover. Everything is fine. We have the resources prepared. And then the MME will finally tell the source eNode B, now we can perform the handover. The source eNode B informs the user equipment with the handover command. Now we do the handover. And you see, this then is a hard handover. Here we perform a hard handover from the source to the target eNode B. The source eNode B then performs status transfer, and all the other devices, they are also involved, that we know, okay, now we are at the new target eNode B. We confirm it, say, hi, it's me. Then we do some final steps, update the area where we are. It's called the tracking area. That's the location area where we are. We can release some resources, etc. So that's the idea. You do not have to know the details of this handover, but that's just the idea. So we prepare the handover in terms of resources needed at the target eNode B, and then we tell the user equipment, now you can perform the hard handover. That looks similar to a hard handover, well, maybe some mixture of GSM, and you could imagine a hard handover in UMTS, but there we had the soft handover. But there's also something new, and that's the handover via this new X2 interface we have here in between. Why do we have this? Well, the idea is LTE can provide something that's called a seamless or also a lossless handover. two different things. Seamless handover, that means we try to perform the handover as fast as possible. Remember, we use packet switching. That means we have to make sure that the new packets are already available at the target eNode B, so that almost without service interruption we can continue, for example, receiving packets. That's one thing, a seamless handover. And the other thing is the lossless handover. Lossless, that means we do not lose packets. With the seamless handover, it could be the case that there are still some packets en route to the old routers. Then we switch over, we have the newest packets, and maybe we drop some packets. I mean, we know this from the internet. Dropping packets maybe is not always a problem. Who cares, maybe for some voice data, depending, we lose some packets. However, you know it from the layer 4 protocols, UDP, we don't care, but for TCP, losing packets, triggering retransmission, maybe we don't want to have this. Maybe we also additionally want to have in-order delivery of all packets, so lossless handover. That's also offered by LTE. So we have to forward the packet maybe to the old and to the new eNode B. We should not lose any packets. And to enable a fast forwarding, to avoid packet loss, the old eNode B can forward the data packet. So as soon as the old eNode B notices, oh, there's no more user equipment, but I still have some packets that are not acknowledged, I could forward them to the new eNode B, that maybe the new eNode B, the target eNode B, forwards them to the user equipment, then they will be acknowledged. Or the new eNode B just stores them, and the acknowledgement of the packets the old eNode B sent to the user equipment will then be received by the new eNode B. We can also perform selective retransmissions. So all mechanisms you know from the internet. So here, basically, you also perform maybe just among the eNode Bs things like, okay, measurement tells me signal's too weak. We decide go for handover. We send this handover request. Yes, we involve the MME, but you see these control loops are way shorter. We issue the handover command, also hard handover. Hard handover, but then basically within this dashed box, we do this data forwarding using the X2 interface, avoiding data loss. That's the idea. And then we complete the handover and do some final things like resource release and switching paths, etc. So that's the idea, that we can perform a handover with the support of the X2 interface, and then the future packets will then be routed via whatever, depending on what is the optimal path inside the network. So you see, there are some features known from the old networks, but also some new features to enable, for example, faster, seamless, or lossless handover using packet switching. No more circuit switching. Maybe you remember what we had to do for handover using circuit switching in GSM. That was also quite a lot. Some questions, some tasks. So please compare the architecture of LTE, UMTS, GSM. What is new? What is basically the same? Then you will understand this evolutionary path when it comes to the architecture, but also the introduction of some new things, like, for example, X2, the X2 connections. So why do we have them? And how can we support seamless and lossless handover? Think of, we have packet switching. When it comes to the access scheme, how can we guarantee data rates? How can we guarantee certain delays? You will learn that in the end, the scheduler has to do a lot. Now compare multiplexing and multiple access schemes in LTE with the UMTS, GSM. What are differences? What are similarities? You will see, the system really made a transition from 3G to 4G, but also has some similarities with some older systems.